The formal definition of heat capacity. Remember in the last part of the lecture we said that heat capacity, we just threw it out, had units of joule per Kelvin, sort of at an introductory level. Actually, the formal definition of heat capacity at constant volume is this. CV is how U changes with T at constant volume. Maybe you're not familiar with this notation. Here we have this symbol like this, whereas we've introduced, and maybe you're most familiar with the symbol like D, infinitesimal change. This also means infinitesimal change, but it means that there's actually more than one variable, and in fact you're taking the derivative with respect to temperature when in fact it depends upon two variables, temperature and pressure. Oh, something depends on two variables? That means we're talking about calculus of several variables. So calculus of several variables. There's I think it's Math 223 at Binghamton University that concentrates on calculus of several variables, but you may have had an introduction to that in Calculus 1 and 2. Let's talk about one variable. We said, for example, we have a function of one variable, f of x. An example that will be a linear function, f of x is equal to mx plus b. You can also have functions of more than one variable. Let's look at two variables. You then would write that a function of, say, x and y. And a function of that mean f of x might be, say, m1 times x plus m2 times y plus b. So two variables, x and y. And given a particular value of x and y, you can then calculate the value of the function. If we just plot f of x on a graph versus x, depending what function it is, we'll get something like that. If we try to plot, this should be f of x and y, a function of two variables. If we try to plot the function of two variables, we'll need actually three dimensions. We have x and y. Those are our two independent variables, and our dependent variable will be the third axis where the function is calculated for some x and y. So this will describe that, and so on. For three variables you need a four-dimensional graph to show that, and so on. Okay, so we're talking about calculus of several variables. Over here we can say the derivative of the function f of x with respect to x, and that is equal to, something you can calculate using what you learned in calculus. There we go, f of x. Over here, how do you talk about derivative of a function with respect to some independent variable? Here we just had one is unambiguous. Here, are we going to talk about the derivative with respect to x or the derivative with respect to y? That's where that simple partial derivative comes in. Partial derivative of f of x, y. Let's take it with respect to x. That means we're considering y a constant. So that's how you'd write that. So this means you have a function that has more than one, as a function of more than one variable. So this means you're taking the derivative with respect to one of the variables and holding all the other variables constant. So when you take the derivative, just consider that as a constant. Similarly, you can write a derivative of a function of two variables with respect to the second variable and holding the first one constant. So that's where that symbolism comes from. Now, what does it mean holding, say, y a constant and take the derivative of x? Well, holding y as a constant means essentially you have some sort of plane here. I'm not very good at drawing a plane, but at a constant value of y, you will define a plane here, and projected on that plane will be f of x, a function of one variable, at that particular value of a second variable. So really you're taking the three-dimensional and slicing it up by holding one, and you're putting the slices perpendicular to the axes that you're holding constant to convert this three-dimensional into a two-dimensional, and then you look at the function right on this plane here and then take the derivative. So essentially that's what you're doing. This then is a specific case of the more general case where you're taking planes, slices out of the three-dimensional space. All right, so that's what that means. Now, writing it this way, we imply that U, remember U was the internal energy, or the energy of the system, is a function of two variables, temperature and volume. And we'll look at that more carefully later on. Okay, so we have U is a function of those two variables, temperature and volume. So we can take the derivative of U with respect to temperature, and I'm using this symbol because we have a function of more than one variable at constant volume, or we can take the derivative of U with respect to volume at constant temperature. So here we're taking slices through the v-axis, here we're taking slices through the t-axis. All right, and we're going to define this as a heat capacity at constant volume. There's constant volume, there's constant volume. So how the internal energy changes with temperature at constant volume is the constant volume heat capacity. So if you think this number is very large, so you have a very big change with temperature at constant volume, then you have a large heat capacity. All right, so that's what that means. Now let's do an example. We'll learn in statistical thermodynamics in our 2 lectures at the end of the course that the internal energy of n moles in a monoatomic ideal gas would be approximated by, say, helium, is 3/2 nRT. What is the heat capacity at constant volume of a monoatomic ideal gas? All right, so we have the internal energy is that. So for a monoatomic ideal gas, the internal energy U is 3/2 nRT. 3/2 nRT. So what is the heat capacity at constant volume? Well, heat capacity at constant volume is the derivative of U with respect to T holding V constant. So the derivative of U with respect to T holding V constant is a derivative of 3/2 nRT. I should really be talking about partial derivatives. Partial means it's not a total derivative, but it's partial with respect to just one variable with respect to temperature at constant volume. Note that volume doesn't appear in here, so we don't need to really worry about that. It really doesn't have to be a constant volume. So the derivative here with respect to temperature is just 3/2 nR. So that's the heat capacity at constant volume of a monoatomic ideal gas. All right, so that's the formal definition of heat capacity at constant volume. And actually we'll have a similar definition when we talk about enthalpy, heat capacity at constant pressure, but we'll have to introduce enthalpy first. We'll do that later on. So that's that slide. We know what the formal definition is, and we did an example for monatomic ideal gas.